Okay everybody, let's go through the solutions to example sheet 4. So if we look at question 1, then basically this is just giving us a travelling wave equation, which is y equals 0.4 sine 247 pi times by t minus 0.07 pi x. So if we give an equation like this, the first thing to do is kind of identify what some of the key constants of the equation are. Because for instance from the class we know that the standard form of a travelling wave equation is equal to y equals a sine brackets omega t minus kx, where omega is the angular frequency and k is what we call the wave number of the wave, which basically tells us how long each waveform is in the wave equation. So from this we can immediately start to identify what the terms are in our provided wave equation here. So we can say that straight away that the amplitude is going to be equals 0.4, because basically this sine function here is just going to give us a sine wave type function, so we can scale that in the vertical direction by this multiplier here. So that's going to basically control the amplitude of the wave here if we draw that on there. We can also see that the omega term here is going to be equal to 247 pi, and the wave number is going to be equal to 0.07 pi. So we're going to identify all those constants. So basically part A of this question is asking us to calculate the initial displacement of the wave at the source at time t equals 0. So basically what that's telling us is that t equals 0 and also x equals 0 because it's at the source of the wave. So if you imagine we go back to our wave here, if you imagine this is distance from the source, then at the source x is going to be equal to 0, and as we move away from the source x increases. So in this case x is going to equal 0. So basically we just need to put these values into our equation here, and of course if we're multiplying this first term by 0 and the second term by 0, this whole bracket is going to equal 0, which means this sine function equals 0, so our initial displacement has to equal 0. So basically we can put all those values in there and we can just see that y is going to be equal to 0 meters. And that's what you should do for any wave equation where you're given the time since the wave generation started and the distance from the source. So you can just substitute those values into your wave equation, and that will give you the displacement at that given time and that given location from the source. So if we then look at part B, it's now asking us for the frequency of the wave. So we don't have the frequency, but we do know what omega is from what we did up here. So basically the frequency is just equal to omega, which is the angular frequency, so the number of radians per second. But if we want an actual frequency, we just divide that by 2 pi. So it's doing a certain number of radians per second, but if we divide that by the number of radians in a circle, which is 2 pi, then that gives us the actual frequency. So imagine how many times it goes round that full circle, which is what we define the frequency as. So we can put that into our equation here. So it's going to be equal to 247 pi divided by 2 pi, which is going to give us, so basically the pi's cancel, so it's 247 divided by 2, which gives us the answer of 123.5 hertz. Okay, so moving on to part C, similar to the previous one, and we don't have the wavelength, but we do have the wave number. We've calculated k here. So we can say that the wavelength in this case is equal to 2 pi divided by the wave number. So this is a standard formula that's given in the exam, which is going to be equal to 2 pi divided by the wave number, which is 0.07 pi, which is going to give us an answer of 28.6 meters. Right, okay. Once again, it's a good idea, just double check your equation and check that the answer looks right. So here we're dividing by a very, very small number, so obviously that number is going to increase a fair bit from 2 to 28.6. So moving on, let's have a look at part D, where it asks us what the velocity of the wave is. Well, if there's one equation you learn in this whole course, it's the wave equation. So here we know that c, the speed of the wave, is equal to the frequency times by the wavelength, which is equal to 123.5 Hertz times by 28.6 meters, which gives us a total value of 3532 meters per second. And then the last part of the question, part E, is asking for the first time at which y equals 0 for a detector placed 0.3 meters from the source. So we need to go back to our equation here, and we basically we can rewrite that. So well, what we can do actually here is if we define if we put our values into the equation here, we can start to see how that pans out. So basically we're saying that y is equal to 0, so 0 equals 0.4 times by sine of 247 pi times t, but so it's the t that we're being asked to calculate in the question, so it's 247 pi t minus 0.07 pi times by x, but we're given x in the equation because it says a detector is placed 0.3 meters from the source, so it's that times by 0.3. Okay, so that's the equation that we're trying to solve. So basically what we need to do is rearrange this in terms of t. But what we can say, or a kind of shortcut, is basically for this equation to be true, then basically for the y value to equal 0, then this sine function here has to equal 0. Okay, so basically this 0.4 can only be, or this side of the equation can only be 0 if we reduce this sine function to 0. So in that case, we can basically argue that sine 0 is equal to 0. So for what's in the bracket here to equal 0, then basically this value here has to be equal to this value here, because if we've got one value and we subtract it from itself, then that makes this whole bit in the brackets equal to 0. So effectively 247 pi times by t is equal to 0.07 pi times by 0.3. Okay, so t is equal to 0.07 pi times by 0.3 divided by 247 pi. Okay, and if you calculate that, then you get a value of 0.00085 seconds. Okay, so that's basically how we can do that. Right, so question 2 is asking us to use the same wave as in question 1. So just to remind ourselves, the equation was y equals 0.4 sine 247 pi t minus 0.07 pi x. Okay. And what it's asking us to do is calculate the phase difference between the displacements at x equals 0.4 and x equals 0.5. So phase difference describes a number of different things to do with waves. If we have two waves, something like this, that are equal in terms of their constants, so they're the same omega, the same wave number and the same amplitude, then basically we can describe the phase difference between the waves as the kind of shift between the alignment of those two waves. Okay, so that's one description of phase difference. But also the phase difference can be described for a single wave as basically the offset between 2 points on that wave. So for instance, if I have a point here and a point here, then the phase difference I can describe as this kind of distance here between the two. Okay, so we can define the phase of a wave, and that allows us to calculate what the phase difference is going to be. And the phase of the wave is just determined by what goes in the brackets here. We can simplify the equation for a wave to y equals a sine of phi, where phi is the actual phase of the wave at that given point in time. So what we're being asked to do here is calculate two displacements on the wave and work out what the phase is between them. But as the phase is described by this term here, we can work out our two phases for each one of the cases that we have up here. So if I call phi 1 is going to be equal to 247 pi t minus 0.07 pi x. But we have a problem here in that I'm being told two new displacements of 0.4 and 0.5 meters, but what I don't know is the a value for t here. And the answer is that actually we just need to choose a constant value for t, and then we can calculate what the phase difference is associated with these two displacements. So what we can do in this case is actually assume, well, to make the maths easier, that t is going to equal 0. Okay, so then we're just considering this part of the equation. So if we consider that t equals 0, phi 1 is just equal to minus 0.07 pi x. So I'll choose the first value, which is 0.4 meters, and that gives me a value for the phase in this case of 0.028 pi. And if we do the same for phi 2, that's going to be equal to minus 0.07 pi times by 0.5 meters, which in this case is going to give me a value of minus 0.035 pi. Okay, so it's negative there. And so the phase difference is just the difference between these two. So if I take one and subtract the other, so if I just call that phase difference, is going to be equal to minus 0.028 pi minus 0.035 pi. Then I'm going to get an answer in this case of 0.007 pi. So if we multiply that together, multiply by 3.14, then we get an answer of 0.022 radians. Okay, so that's basically the difference between the two phases to answer that question there. Okay, so then we'll move on to the next question. So here we're being asked to, I'll go into a new sheet of paper actually for this one. So for question 3, we're given a range of lights in terms of frequency. So f1 is equal to 530 terahertz, and f2 is equal to 600 terahertz. And so we're told that green light sits within this range. So basically we're in the range where the frequency is less than 600 terahertz and greater than 530 terahertz. So you think about this as the diagram of the electromagnetic spectrum, where certain portions of that spectrum correspond with certain types of electromagnetic radiation. So all we need to do here is work out what the range is here, but in terms of wavelength. So basically we need to work out what the high range is and what the low range is for wavelength. So what we're going to do is just convert this into wavelength, because we know what the speed of light is, and we can therefore use the wave equation to calculate this. So our wave equation tells us c equals f lambda, so lambda is going to be equal to c divided by f. So f1 here, the lambda 1 equivalent of that, is going to be equal to 3 times by 10 to the power of 8 divided by 530 terahertz, which is going to give us a wavelength of 500 nanometers. And then lambda 2, so it's 566 nanometers. And then lambda 2 is going to be equal to 3 times by 10 to the 8 divided by 600 nanometers, which in this case is going to be equal to 600 terahertz. which in this case is going to give us an answer of 500 nanometers. Okay, so basically the range that we defined before in terms of wavelength is basically the wavelength is going to be less than 566 nanometers and greater than 500 nanometers. So that's the solution to that question there. Okay, so for question 4, we have a light bulb, and that's emitting power in all directions. So imagine the light is kind of radiating away from this point, and at a point 3 meters away we have a small circular sensor that's facing the light bulb. Okay, so that's what's recording the energy at that location. So there's a couple of different ways we can calculate what the recorded power by this detector is going to be. The first thing you can say is, well, basically the power is being radiated equally in all directions. So if you imagine a kind of spherical surface at a known radius from that bulb, then all the power that's emitted from the bulb has to pass through that surface. So it's kind of shared over that area, which is what determines the intensity of the light. So we can argue that the ratio of the areas of the large sphere that all that 60 watts of power is kind of passing through, relative to the area of the detector multiplied by that power, is going to give us what the actual power is recorded by the detector. Okay, so you imagine like the sun, it radiates power in all directions. We capture a small bit of that being the Earth. And so we can look at this massive sphere around the sun where the Earth sits in space is the area that all the power is moving through, and we capture a small bit of that by the area of the Earth. So it's the same kind of argument here. So so basically the power recorded at the detector is going to be equal to the ratio of the area of the detector divided by the area of this big sphere that 3 meters that away from the light bulb that all that power is passing through. So I'll just call that sphere, multiplied by the initial power of the bulb. Okay, so the power of the bulb I'll put in there. So we need to work out what these two areas are. So that's going to be equal to pi r squared, which is the circular area of that detector, divided by the surface area of this sphere, which is going to be 4 pi r squared, which is the full radius of the sphere. So so that's the equation that we need to use, and we need to multiply that by the power of our bulb, which we've already been told is 60 watts. Okay, so we put our values in. So we've got the radius of the detector is going to be equal to 0.01 meters, because we're told that the diameter of that is 20 millimeters. Okay, so 20 millimeters is 0.02, the radius is 0.01, and then the radius for this bottom part, I suppose a better so RD and RS, the radius of the sphere in the bottom part is going to be equal to 3 meters, because that's what's given in the question. Okay, so if we put the numbers in there and multiply that through, then we'll get the answer of 0.00167 watts, which is equal to, as we've converted there, so 0.167 milliwatts. Okay, so that's one way of doing it. The other thing you can do, or perhaps the easiest way for some people, is you can calculate the intensity of the energy. The intensity decreases as you move away from an object, because obviously these kind of imaginary spheres with which the power is passing through are getting larger and larger, and we basically define the intensity I is equal to the power divided by the area over which that power lands on. And this is why, as we move away from an object, particularly if it's hot, it starts to feel much less hot, because basically we've got we're increasing this area over which that power is being transferred through. Okay, so what we can do is, first of all, we can calculate what this intensity is going to be at this distance from our light bulb here. So basically, at a point 3 meters away, then the power is going to be 60 watts as it was before, and the area is this sphere that we defined before, which is going to be 4 times by pi times by the r squared. So that's 4 pi times by 3 squared. Okay, so if we put those values in, then we get an intensity at 3 meters. It's going to be 0.53 watts per meter squared. Okay, so that's the unit of intensity because it's just the power divided by the area. So the area has to be meter squared. So that's basically telling us what the intensity is at this location 3 meters from the light bulb. Okay, but that doesn't really tell us anything about the power that's being absorbed by the detector at this stage. What we need to do is go back to relating power and intensity together. So if we want to go the other way, the power is equal to the intensity multiplied by the area over which the intensity of that radiation is absorbed. So this is why the power generated by solar panels actually doubles if you double the area of a solar panel. So okay, we're on Earth, we have a solar panel that's pointed at the sun, but we're way, way away from it. We can calculate the intensity of the sunlight on the Earth's surface, and the power we generate is then proportional to the area of the solar panel. So in this case, the power absorbed by the detector is equal to the intensity of the illumination at the detector, as we've got here, which is 0.53, multiplied by the area of the detector. So once again, that's times pi, r squared. In this case, r is 0.01 meters squared. So that's our equation. And if you calculate that, then we get exactly the same value that we've got up here. It's going to be 0.00167 watts, which is 0.167 milliwatts. Okay, so that's how we solve that question. And then if we move on to question 5, we're now looking at refraction. Okay, so once again, it's a good idea to sketch out what's happening in the question. So here we have the surface of a pond, we have a ray of light is coming into that pond, and what's going to happen is when it hits the surface of that pond, it's going to refract. So if I put a normal on here and here, then I would expect the light ray, as we're moving to a denser material or medium, to bend in that direction. I'm also told what the refractive indexes are of each material, so that is n is 0.1, and the bottom n is equal to 1.5, which is normally representative of glass, but it seems a little high for water, but never mind, we'll continue with the question. We know this angle here is equal to 20 degrees, and we want to calculate this refracted angle here, I'll call theta r, based on the system that we have here. So the way we do that is we use Snell's law. So basically, Snell's law suggests or states that the refractive index. If we have the incident angle, if we take sine of that, sine theta, if we multiply that by the refractive index, and that's going to be equal to the refractive index of the other material times by the sine of the refracted angle. So I'll just put an I and an R to indicate that's the incident angle here, and this is the refracted angle that we see there. So we can rearrange that. So basically we want to calculate theta r, so we can say, well, sine theta r, if I just divide both sides by n2, it's equal to n1 sine theta 1 divided by n2. So basically theta r is just going to be sine to minus 1 of n1 sine theta 1 divided by n2. Okay, so that's our equation. And so all we need to do is put these values in. So n1 is 1, so that's just sine theta 1 divided by theta 2 is 1.5. So sine theta divided by 1.5, which gives us the value, as you see in the equation, of 13.18 degrees. Okay, so it's just a simple application of Snell's law, which, as I say, is given in the example formula for the exam. Okay, so now we're going to look at question 6. So basically what we have here is we have a glass plate surrounded by air, but then on the back surface of this glass plate there's a reflective layer, so it could be sprayed on silver or something like that, which is exactly how they make mirrors. Basically with a mirror, you normally have a very flat piece of glass, and then what you do is you coat one side of the mirror with a highly reflective paint, and that's what forms a mirror effectively, which is what we have here. So what we're being asked to calculate for this question is we have a light ray comes into the surface of the mirror here, it's refracted, it reflects off this bottom surface and reaches a point at this point here on the air glass interface, and we're being asked to calculate what this distance is, x, between the point at which it enters the mirror and the point at which it comes out again. So we have to think about how we're going to do that and what we can calculate. Well, we know that this ray here is entering an angle of 38 degrees, so if we understand the refractive indices of these two materials, which are given in the question, so air n equals 1 and here the glass n equals 1.5, then that gives us the information we need to calculate what the angle is here, which is theta r, which is our refracted angle on the diagram here. We also know that from the law of reflection that the angle of incidence has to equal the angle of reflection here. So basically this value, if I call that phi, has to equal this value here, so I'll call it phi as well, because those two angles are equal because of that law. Another I can say as well is if I extend this normal up here and extend the normal down here, this forms a z angle. If these two sides are parallel, then this angle has to be equal to this angle here. So basically the refracted angle theta r has to be equal to phi, and then this gives me a right angle triangle here. So I know what the angle is phi here, and I can use the properties of this right angle triangle to calculate a distance a, which is going from this line to this line here, okay? And then if I know what that distance a is, I can double that because this triangle is just a mirror image of that triangle, and that will give me this value x. So let's work through it step by step. So to start with, let's work out what this angle, this refractive angle here, theta r, and this is the same as the solution to the last question. So just to rearrange Snell's law, and we get that the theta r is equal to sine to minus 1 of n1 sine theta I, the incidence angle, which is equal to 38, divided by n2. So if I put those numbers into the equation, it's going to be equal to sine to minus 1 of 1 sine theta I divided by n2, which is 1.5. Okay, so that's going to be my calculation there, and I can put the numbers in this equation here. So that's going to be 38 degrees, and that gives me a value of 24.5 degrees is my value of theta r, which is here. So I know that angle there, which means that phi here, this angle has to also be equal to 24.5 degrees, because these are sort of corresponding angles if these two sides are parallel. Okay, so that allows me to define this right angle triangle here. I know this angle is 24.5 degrees. I don't know the length of the hypotenuse. I do know the length of this adjacent side though, because it's the thickness of the glass plate. So the adjacent side length is 1 centimetre, and what I want to do is I want to calculate the length of the opposite side. So if I know if I have the adjacent side and want to calculate the opposite side, then the best trigonometric identity I can use to calculate this is going to be tan. So tan of this angle phi here is going to be equal to the opposite side length divided by the adjacent side length, which is going to be equal to a, which is the side I want to calculate, divided by this side length here, which is the thickness of the glass. So that's 1 centimetre, but I'm going to write that in metres because I normally do. It makes me feel more comfortable. So I also know this angle here, phi, is equal to 24.5 degrees. So let me rearrange this equation. So a is equal to 0.01 times by tan of phi, which is 24.5 degrees. Okay, so I can calculate that using that there. And if I calculate that, then I get a is going to give me a value of 0.0045 meters. Okay, so but going back to my diagram here, I know that x is going to be equal to double a, because that side length there is going to be a as well, because that's just a mirror image of the triangle that I've been using. So basically x is equal to 2 times by a, which is 2 times this, which is going to be equal to 0.009 meters, or I can express that as 9 millimeters. Just multiply that by 1,000, because there's 1,000 millimeters in a meter. Okay, and that's it. That's a solution to part 6. So they're the full solutions for example sheet 4. If you have any questions about those or need further clarification, then send me an email. Okay, thank you.